Start, ma'am.
Welcome to this live session on the course Biochemistry 1. We understand that during the pandemic situation, you have gone through a lot of difficulties, but nevertheless, online classes have probably been more appropriate at this point. And now that you have these online lectures for you, we hope they have been helpful to you from the NPTEL sessions. We will start our live discussions on the questions that have already been posed in the Google Forms, which I will share my screen. We have written out the answers to the ones that we have already received, and following that we will go for a chat session. So those of you who do have questions, please write your questions in the chat boxes so that the TAs can transfer them to me, and then we can go about trying to address the queries that you may have. I will share the screen and try and explain the sort of queries that some of you had relating to the different structural aspects, relating to the course aspects, and also relating to the exam propositions. The question that we had for one of them was, can the molecular formula, as you can see here, can the molecular formula of hemoglobin be only experimentally determined, or its CHSNO composition be understood by breaking its structure into rings? Now, we know that hemoglobin is a tetrameric structure, and each hemoglobin we know is comprised of what we would say the 4 heme groups that we see here. So the 4 heme groups that we see here are surrounded by a globin group. So the hemoglobin is this tetrametric structure that we will be seeing. Let me see, I just want to scroll my okay. So what we see is we have this porphyrin ring. So when we look at the heme molecule itself, it is the organic compound that is known as the porphyrin, which is attached to an iron atom. Now this porphyrin ring we know has the iron atom that is present here, and it is connected to several amino acids in the protein. Now this is extremely important in the way it is held in its scaffold in the protein for its proper action in the way it has to bind the oxygen. Now, when attached to the iron, this porphyrin becomes what we know is called the heme. Now, you understand that at every point in time when we are trying to describe a molecule, or where we are trying to describe what the protein looks like, it is difficult to draw these porphyrin structures or to indicate where the iron is, and so on and so forth. So what we do is when we write HEME as the heme, we know what we actually mean. We know that this heme means that the porphyrin has an iron attached to it, and that is good enough to understand that we have the heme with us. Now, if we also look at the state of when we write would be a similar question would be that if we would want to have the polypeptide chain. Now, if I have the polypeptide chain, as we have explained in class, we do not write the whole amino acid sequence in the terms of all the atoms that are present. What do? We look at 3-letter or 1-letter codes that tell us that this is the polypeptide chain, because all I need to know is I know the basic structure. I know that it is connected by the peptide bonds, and all I have to do is just write the sequence of the amino acids, and based on that, I know exactly how they are connected and how they should be drawn. On the other hand, the same thing happens when I say that there are, say, 4 heme attached to the hemoglobin. Now, there is 1 heme in each subunit of hemoglobin that we know contains 2 alpha and 2 beta. And we can get this tetrameric structure from the protein data bank. So what we know is we write the form we write a polypeptide chain in the form of its sequence, either in 3-letter code or in 1-letter code. And when we have a larger, we will see a prosthetic group or a cofactor, then we just write the short form of it, because as a biochemist, as one who is studying biochemistry, you will know that this is the way we represent the molecules. So the representation is important, and the representation is universal. We will go on to the next question, how you can calculate the number of isoprene units. Now, this terpene is composed of we know that terpene itself is composed of 2 or more isoprene units. Now, what is this isoprene unit? We see that we have one, there is a double bond here, then there is a single bond, and then there is a double bond. So this number is numbered 1, 2, 3, 4. Now, when we link these two together, they can be linked in a 1-1 manner, or in a 1-4 manner, or in a 4-4 manner. So when we look at these terpenes, the naturally occurring terpenes, we have what is called a 1-4 linkage, which we see as a connection here, a 1-4 linkage that is depicted as this form, and the connection shown in red is the connectivity that has been obtained because of the connection of these two isoprene units. So to obtain the number of isoprene units in a terpene, it is best to count the number of carbon atoms and to account for the number of double bonds present, and that would give us an idea of how the connectivity is in the isoprene units, say in a terpene. Our next question was to explain the anomeric effect through an orbital diagram. Now, what is the anomeric effect? The anomeric effect describes the tendency of these heteroatomic substituents that are adjacent to a heteroatom within a cyclohexane ring. So this is a cyclohexane ring, and whether our connection would prefer what is called an axial orientation. So this is an axial bond, and this is an equatorial bond, and this is an axial bond. Now, when we look at when we represent a molecule like this, we know that this is the carbon atom. This carbon atom, so if you look at this particular carbon atom that I have drawn here, this carbon atom is connected to this carbon atom. It is connected to the far side carbon atom, and in addition, it has 2 hydrogens. We know that this is sp3 hybridized, so the representation is such that we have the 2 hydrogen atoms linked on one on this side and one to the bottom. So there's one this side and one this side. Now, when we are looking at this, we try to explain the steric considerations and then determine what is convenient or what is appropriate for the molecule to be in its basic native form or in its most stabilized form. So when we look at the structures like this, if we know now that we have a hydrogen atom here we have a hydrogen atom, here we have a hydrogen atom. So how would the molecular functional groups that are attached to the basic ring, how would they preferably be in the molecule when we consider the steric considerations? So here in this case, there are 2 ways. We have one in A and B set, one in an X and Y set. Now, this has an oxygen atom here. This does not. Now, what would we say would be preferable for a molecule to exist in? In the case of A and B, A would be favored. Why? Because it would be less hindered, less steric hindrance. However, in the case of X and Y, Y is more preferable. Now, why is that? This is because there is something that we call hyperconjugation. Those of you who have studied some basic organic chemistry would know about hyperconjugation, where there is a connection between the unshared electron pair on the endocyclic heteroatom. That is, what does that mean? It means the endocyclic, that means it is part of the cycle, the cyclic part that we have here, the endocyclic ring, and in this case, the oxygen, and the sigma star orbital of the axial COCH3 bond. So the molecule would prefer the alignment where the donating lone pair of electrons is anti-periplanar, that is 180 degrees to the COCH3 bond. Because ultimately what we want is we want an overall energy of the system to be low, and that would stabilize the molecule. So if we look at this set where this is where we have the sigma star, and this is where we have the two lone pairs. Now, when we look at a situation where there is favorable orbital overlap and hyperconjugation possible, this makes this particular molecule more stable than a one on the left, which is why when we look at these two structures, in one case we would have the equatorial one that would be more stable. In one case, we would have the axial one that would be more stable. The next question that appeared on the Google form is how can we identify reducing and non-reducing sugars? Now, what is a reducing sugar? A reducing sugar is one that can reduce a mild oxidizing agent, and what can do is there are specific tests for this. And what are these tests? The tests tell us that when we look at copper sulfate in alkaline tartrate, or most of you might have looked at a formation of a silver mirror, a reduction of the silver nitrate forming a silver mirror. Now, if it is possible for a reducing sugar to be oxidized by this mild oxidizing agent, then we would be able to identify it. How can we identify it? So a non-reducing sugar is one that would not be able to reduce this mild oxidizing agent. So if we look at an aldohexose, what is an aldohexose? An aldohexose means it has an aldehyde group, and a ketohexose would mean it had a keto group. Now, when we look at this particular carbon atom, we know that this carbon atom has 4 valences. So we have this carbon 1 attached to number 2. This carbon has 2 bonds to the oxygen. So the one left that has not been depicted is the one that has the hydrogen in it. So what would we mean a CHO correspond to? A CHO corresponds to what an aldehyde is, right? And this aldehyde group can act as a reducing agent with the specific given reagents as have been mentioned on the top. And as a result, glucose gets oxidized. Now, this is true for most monosaccharides. The aldoses act as reducing agents directly. And if we have the ketoses that would have the double bond O, that would tautomerize into what is called an enolic form, and then it would act as a reducing agent. But when we have disaccharides, that becomes a problem, because not all disaccharides can be reducing agents. So how do we identify that? Now, it so happens that, say, we're looking at sucrose on the left and lactose on the right. Lactose on the right. On the lactose is a reducing sugar, but sucrose is not. Now, we know that sucrose is a combination of glucose and fructose, right? Now, when we look at lactose, we have the disaccharides. We have to check whether the carbonyl carbons, what do we mean by the carbonyl carbons? The C double bond O's, whether they are free or involved in the glycosidic linkage. In case of sucrose, what happens is both of these are involved in the glycosidic linkage, so they are not free. If they are not free, they cannot. The one that we can see by the lactose that is there is free, so the one that is not free cannot be involved in the reduction or the reduction to form, say, the silver mirror or any other reagent that we might be looking at. So whether it is a reducing sugar would be dependent on whether the carbonyl carbon is free or not. And in disaccharides, what happens? They may connect to each other and not remain free. The next question is, what is mutar rotation? Now, when we look at mutar rotation, it is alpha and the beta forms where we look at the position of where the OH is. So here we can see the OH in a down position, in an axial position, here the OH in an equatorial position. And what is this rendered? This is rendered by an alpha D. What do we understand? This is glucopyranose. What do we mean by pyranose? A 6-membered ring. And what is furanose? Or then we have a furanose and we have a pyranose. Now, when we have alpha glucopyranose or beta glucopyranose, we have the anomeric carbon. So this is the anomeric carbon. Now, the rotation of this specific rotation of alpha is plus 112 and this is plus 119. So what happens is when there is a mixture of these two, then there is a possibility of what is called interconversion. Now, what happens is the optical rotation therefore changes when one is shifted to the other. As a result, what happens? The optical rotation undergoes a change and there is a change in the equilibrium mixture concentration of the alpha glucopyranose and the beta glucopyranose. As a result of which, if we do not have a pure solution either of alpha or of beta, but we have a mixture of both, there is a change in the optical rotation, and this change results in what is called equilibration, and this equilibration leads us to a intermediate value of the specific rotation, as some of the alpha form will be converted to the beta form, and as a result, this equilibration would give us what is called the mutarotation property. So if we just want to combine all the information that I just gave you, it would be that mutarotation is when the two anomers that have different specific optical rotations are allowed to equilibrate. They would lead to a different optical rotation that would be a result of the resultant solution that would be possible because of the transformation or the transforming of one type to the other type. The question was, how do we remember the structure of carbohydrates? Is there any trick? Well, there is no easy way as such. The best way would be to know what an aldose is, what a ketose is, and what we mean by the L and the D form. Okay, so this is the best way to look at it. So we look at the OH attached to this last position here, the one that is attached to the CH2OH, in this case, the 5th position here, and then if the OH is on the left, we would call it the L. If it is on the right, it is the D form. Okay, so, and then obviously we would try and remember these specific positionings of the OH and then talk about whether it is arabinose or glucose and so on and so forth. So when we're looking at a situation like this, we have this on the 4th carbon, the penultimate carbon here, which would be on the left. So this would be L-arabinose and this would be D-arabinose. But to say that there would be an easy way to remember this is probably not very convenient in this case. The question now goes to what the pattern of the questions for the final exam would be. They would be the same as what you have in your assignments, but obviously a bit more reading and a bit more involved. So I would request you to read the questions carefully so that you can address them. They are all from your lectures and some of them from the assignments that you have been doing weekly. The next question was, what is the meaning of the central dogma? Now, the central dogma is a part of biology, molecular biology, that takes us from the DNA to RNA to protein. And this is what makes us what we are, involved in all living organisms. The central DNA, that is the genetic information, the transformation, or the transcription of the DNA to the RNA, and then the translation of the RNA to the protein, which is the most fascinating transformation that is possible or that is known. That is what we can now do with molecular biology techniques, is from a DNA, as you know, a recombinant DNA, we can actually make proteins. And this is extremely important for research purposes, where we can actually make a protein to understand or to try and develop inhibitors, as you have studied in the enzyme classes related to the enzymes. When we're looking at these enzymes and we want to combat disease and we want to prepare such molecules that we can test for the different compounds that are made to see whether we have effective drugs for several diseases, then we need a lot of the protein. And it is not always possible to get the human protein for a correct testing. So what do? We make the protein. And this is possible because of this DNA to RNA to protein, a knowledge of the DNA sequence that leads to a knowledge of the RNA sequence that will give us exactly what the protein sequence is. And the way the protein is formed, I read a question somewhere in one of the chat boxes where we have the nitrogen. Like, why does the protein? That is the way the protein synthesis occurs. It starts off with the N terminus and ends with the C terminus. For those of you who it would be possible, a very good idea would be to check how protein synthesis occurs there are many animations available. You can just look for a protein synthesis animation and just see how beautifully a chain is formed, a chain is folded, and the protein three-dimensional structure is obtained. So we have the central dogma that gives us a detailed residue by residue transfer of sequence to information. The next question was related to a single sugar and how do we draw the 2-endo and the 3-endo. Now, when we're looking at a single sugar, the puckering usually occurs when it does not want to remain in the strained form. A strained form for a 5-membered ring, for a single 5-membered ring, sometimes would leave the oxygen a bit higher up. So this would be just like if you have an envelope. If we have an envelope, then there are 4, and you have a flap to the envelope. So when we open this envelope, and this is the oxygen atom, it slightly remains higher than the rest of the level of the 4 carbons that we have. But when we're considering situations like this, to relieve the steric strain, we have to see where the crowding is occurring. And based on that, we can define the 3 and the 2. These are the two, the hydrogen, the OH linkage that are there in the ribose. We know that this is a ribose sugar because we have 2 OH groups attached, one to the 2 position and one to the 3 position. Now, when I'm looking at this particular situation and I see that the 3 is pointing outside. So this is where the R group is, this is where the OH is, this is where the 2 OH is. This 2 is endo because it is towards the direction of where the CH3 and the R is, and the 3 is exo. So this would be one sort of a twist. When we look at the other possibility, what we have here is we have the 3 now, which is the endo, and the 2, which is the exo, based on where or which direction it is going to relieve the steric strain. So there can be another way it would do it, as I mentioned, where we are not looking at an 2' endo or a 3' exo or the other way around, but we're looking at the oxygen atom itself actually folding up a bit, where in that case 2 and 3 would be flat and the O would be higher up, because these are common ways in which these sugars actually stabilize themselves. So the stabilization occurs in a way where it could be the 2 endo, 3' oxo, or it could be the 2' exo, the 3' endo forming this particular method. So we understand this part. The last questions that we had were about, this just came a while ago, where we were looking at, you are looking at the eukaryotic DNA. Can it survive in outer space? Well, that's a very puzzling question. We're not very sure about that. Maybe with the new Mars, Perseverance, and these we'd probably be able to see whether there are a lot of space missions and trying to understand these possibilities to see whether the DNA would actually arrive in space. So there is in a paper actually a new study that was actually one of my TAs found out, that published today. A team of Swiss and German scientists report that they have dotted the exterior grooves of the rockets with fragments of DNA to see whether the genetic material can actually survive in space. So maybe you would have to wait a few years, say, or at least a later date to find out whether these would remain. Okay, and whether it could actually, our genetic information could actually get us anywhere, and this genetic information could be brought back with, you never know, with modifications, and it would actually have to survive what is called the re-entry into the Earth's atmosphere. And then we would be able to determine whether your DNA can actually survive in outer space. So then the question was about prosthetic group and a coenzyme. So when we look at these different terminologies to try and understand what they all mean and how an enzyme is to act. Now, for an enzyme to act, it needs sometimes some extra hands. And these extra hands come in the terms of what we would call a coenzyme, a prosthetic factor. Some of them linked, some of them not linked. Some of them would have to remain with the enzyme for all time. Some of them can be shifting from one to another. Some can be present in solution and arrive at the time only when the enzyme has to bind to a substrate for a particular reaction to occur. So these definitions are there in the books, that has been described in the lectures as well. And these are all these helper molecules, or they assist in the biochemical reactions. And the cofactors that we have, it is a non-protein chemical compound or a metallic ion that is required for the enzyme to act. We know that the enzyme is a catalyst. And when we have this particular chemical reaction, or in this case, a biochemical reaction occur, the facilitation of the catalyst is also brought about by these cofactors or the helper molecules that can be of different types. They can be inorganic in nature, like metal ions. They can be organic molecules that are called coenzymes. And coenzymes are divided again into further two types. What are these? These are the prosthetic group, which consists of a coenzyme that is tight or even sometimes even covalently bound, and it is permanently bound to the protein. And some are called co-substrates that are transiently bound. But we have to remember that if these actually take part in the reaction, like we know that when we have an enzyme work on a specific substrate, it has to return to its original position, its original orientation, its original disposition of amino acid residues to actually be able to interact with another substrate. Again, this is the same with these molecules as well, or these particular prosthetic groups or coenzymes, those that are transformed or are changed during the methodology of the reaction or during the biochemical steps or the chemical steps that occur in the enzymatic catalytic reaction, they have to get back to originally where they were. So they can bind very tightly. They can also bind in a manner that is transiently bound, covalently bound, or it would depend upon the type of reaction that actually occurs that would tell us whether this is a prosthetic group that would be bound covalently or a coenzyme that is bound non-covalently in this case. So that would end the ones that we have had so far. And I will now go to the chat and to see whether there are any questions related there. You can have. Do we have any questions in the chat? No questions so far. So That's okay. I guess we addressed most of the questions. There was one related to what a hairpin bend is and about the supercoiled DNA, where in which part of the cell cycle it actually participates in. Well, the supercoiled DNA participates in the S and the G phases of the cell cycle. And if we do not, as far as I can see, there are no questions so far. So I hope this half an hour session was useful for you and we could address most of the questions that you had in the live session. And we will wait for a couple of more minutes before we sign off. Are there any questions on the YouTube session? Have you checked there? Atoshi, have you checked there in the YouTube sessions? Are there any?
Yes, ma'am, I have checked. There is no questions.
There are no questions on YouTube as well. Okay.
Just Hani Sharma asked, ma'am, I'm preparing for IIT JAM. I'm reading John McMurray for biochemistry. Is it good?
Yes, yes, it is a good book. You can also follow the books that we have mentioned in class, such as Leninger, Voigt and Pratt, which is the latest version of Voigt and Voigt. And of course, it would be best to go through the specific question pattern types. That would definitely help you. Yes. Best of luck for your exam. Who is monitoring this at the IIT site?
Ma'am, there is another question from Ayush M. So he's saying, I would like to ask how the hydration cell of sodium and potassium ions impact the transfer of ions in the membrane.
Okay. Okay. So in this case, what would happen is when we talk of hydration, when we talk of the size of the ions, you know that, let me just show you what I mean by this. Just share the screen again. And is my screen visible? Atoshi, can you see my screen?
Yes, it is visible.
Okay. So if I say now, if I say that we have, can you see what I am writing, Atoshi, just to confirm?
Yes, ma'am, it's visible.
Okay, so if we have the Na plus, we have Na plus and K plus. Now, when we're talking about a hydration shell, we know that it depends upon the size of the ions that we have, and beyond this, there would be the hydration shells that would depend upon the size of the ions. Now, the transport of the ions between, when we're talking about an intermembrane transport, we know that we have the specific port that takes sodium in one direction and potassium in the other direction. So that is an important feature that has to be taken into consideration. If, say, we, just for information, say if we argue in the way that we're looking at lithium plus ion, right? The lithium ion plus would have a hydration shell because of its positive charge but smaller size. It would have a hydration shell in a manner that would make its mobility, as we call it, different than those of the sodium ion and the potassium ion. So that mobility is very important. But if we look at the same, in the same argument, if we look at the intermembrane space and we look at the hydrogen or the proton, this is also, it has also a single charge and it is also the smallest, but this travels the fastest. Right? In the same argument, if I'm saying that lithium ion becomes sluggish because of its small size and the single positive ion, in the same argument, I should say hydrogen ion would be the smallest. But the movement of the hydrogen ion, that is very, very important, as you know, in all biochemical processes, actually occurs through a transition in a through water. So at any point in time, this would be connected, this would be like an H, so this would be a plus. So we would have this proton actually, so this proton would be actually hopping to another water molecule. And in that case, what would happen? This, we would actually quote unquote see the hopping of the transfer of the H plus ion much more simply than we would see the transport of the sodium and the potassium ion. Anything else? Now I see a question in the chat box. Ma'am, my multiple select answer type question portion is very weak. How can I increase this? I guess practice does increase this. Another way you could increase it is the main thing that we see in students who attempt multiple choice MCQs, as we call them, is the what would I say, is the hasty way in which you approach them. Because it appears at one point that all the answers are possible. So I would suggest that you read the questions very carefully. Usually you have enough time to answer, but it sometimes so appeals to you that you suddenly circle one and then you are confused. That is the problem I hear a lot of students tell me also. But this multiple select type, a lot of students are not very comfortable with multiple select types and would rather MCQs, or would rather sit and write out an answer, being more convenient. That's the way they feel. There are a lot of students who are really, really good, but when it comes to MCQs, they cannot answer preferably, or they cannot answer correctly many times. So the best thing here is to practice. And as I mentioned, please read the questions very, very carefully, because the questions sometimes are confusing and the answers are more confusing. So because the language is put in such a way so that it, unless you're confident about your answer, you would not be able to pick the correct one. So all the best for your tests. And we will have another live session in maybe definitely before your exams, so we can address any other questions you have. And what I would do is I would tell you to write them in the discussion forum, where your TAs will happily answer your queries. I'm sure they're doing a good job answering the queries as they come. And if all, you can also send, you know, my email address, you can also send me email for specific certain additional things that you might want to be taught or might want to learn about. And definitely before the next live session, I would suggest that you go back to the Google form that will be circulated prior to the live sessions, and pose your questions there, because what happens in that case is then we can address them more comfortably, in a sense, and more thoroughly, because then we would have gone through them and explained the matter better to you. So I guess if there are no new questions, then The pattern of the, I have a question about the MCQ. The pattern of the examination is multiple choice with a single correct answer to each of the questions. But as I mentioned, you have to read the questions very carefully, look at the figures very carefully, and read the possible options also carefully, as they are on the pattern of your assignments, but nevertheless, as they are a final exam, you realize that the questions would be, I wouldn't say difficult, but would be more involved. All the best for your exams. Who is monitoring from the IIT Kharagpur side? Do any of you?
Yes, ma'am.
Okay, I guess there are no more questions, and so can we?
Yes,
It
ma'am.
was.
We can sign off. Yes, ma'am. We can sign off.
We can sign off.
Yes, ma'am.
Okay, thank you. Thank you, Atoshi Shrestha Prashan. Thank you. Okay.